Hello, good morning, everybody. You can see on slide two words. One is Action Consultancy, that's my company. And another word is water, which is recycled water, is the daughter of water named water, pure, pristine, and future. So with sewage treatment class, we want to go toward the journey to create water out of wastewater. So today we'll cover fundamentals of sewage treatment plants. The entire presentation has been divided in various modules, which is called fundamentals of STP, preliminary, primary, secondary, tertiary, waste sludge management, process calculation, troubleshooting, process control, performance management, and management in change. So today we are working on this module number called fundamental of STPs. And the two models which are in the bottom, 10, performance management and management of change. These are very specific models, usually dedicated towards a particular industry. So this kind of training modules we take only when we study that particular plant premises. Suppose, I have studied once 110 MLD Washi sewage treatment plant, and for them I designed this performance management module as well as management of change module, because it varies from municipality to municipality or industry to industry. So in the next 4 days when you are with me, we will go to first 9 modules. Okay, Twinkle. And first module we'll talk about is the fundamentals of sewage treatment plants. What are the aim and objective of the first model? First of all, foremost, let me try to tell you why we treat sewage water. Define current challenges, classify wastewater contaminants and unit process involved. This is a very important section. Please pay attention there. Overview treatment methodology with respect to technology. All entire summary of 9 modules will be presented here. Typical wastewater treatment schemes we'll talk. Complexity of SWT due to intermixing of several processes, physical, chemical, biological. So why this sewage treatment technologies are actually slightly complex. Then understanding the various control factors, and of course, as we can say, question answers. So each session when it ends, when I say each session ends, does not mean each day end. So each session end, we'll have a question answer session. So maybe there could be 2 question answer sessions today, or maybe 3, depending upon at what pace we cover the modules. You do have the right to type something in the chat box, but I'm sorry, I do not have access to the chat box when I'm presenting. Okay, so I can't see that. I'm able to see it on the other screen, but I will not be attentive there. So Ramya is the one. If there is something to be answered immediately on something, you can interrupt me, Ramya. Please be my co-trainer. No problem.
Sure. Mr. Sanjeev, the chat box would be closed. It's inactive for today. Today they have we have it only question and answers window open to all.
Okay.
So anybody, I will let you know.
Yeah. Please, anything comes, somebody wants a repetition on a slide, something, because
Sure.
objective, all the participants, gentlemen, I don't know how many of you are listening to me, but all the participants, idea is not that I train. There's no idea. I have trained many times, many people. Idea is that you learn. So if there's any doubt, please get it clarified. This is your opportunity. Okay. So let's enjoy this program today. So if you ask me, why do you treat sewage water? And the answer is in a very simple diagram. When you look at this diagram, you will find that our interrupted water supplies are all interconnected. You can see, right? Industry will use water, which will come from the same source. They will use the water, put a wastewater treatment plant, and put everything to the receiving water body. Same receiving water body will supply water for municipal water treatment plants. They will purify it to a level so that we can drink and take bath into that. And they must treat via sewage treatment plants and put it back into the recycle loop. Again, the same water you take. So this is what is a recycle loop. Be it a river, be it pond, be it lake, the loop is same. What happens is some loops are not loops in nature, but series in nature. For example, river. So the effect of not treating sewage in Delhi may not affect Delhi, but will affect Agra, because the sewage has reached Agra city. The effect of water again drawn from Agra not being treated, goes to further down the town, you will reach Kanpur. And you reach Kanpur, Ganges path I'm talking about. In there is a Tanneries cluster. They will take the water again from where? Ganges, no other place. And they'll put the effluent back where? Again Ganges. So water is a finite resource that we continuously reuse. So this word of water use and reuse, no, you forget it. We always reuse water. Whatever water I am using today, even for drinking purpose, has been used by somebody else. Please believe me. This is not a new water generated by God for me. It is a water continuous reuse. So sewage water generated by us ultimately becomes the feed water to us. This us could be two different places, right? What we throw in a sewage treatment plant in Delhi becomes drinking water in Agra. That's the reality. So we continuously reuse the water. It is not that we get any fresh water for our civilizations. So this is something which you have to understand and keep advocating throughout your life. And technologies today must protect public health and environment. See, what is the purpose? A lot of time people tell me, Ki, Sanjeev sir, give me hi-fi technology. There's nothing called hi-fi technology. The right technology is a technology which protects public health as well as the environment for the next generations to come. So with this small introduction on why we need to treat sewage, we go further on. You can see sewage water polluted river. The new norms of STP, Hindustan Times news cuttings. STP reduces the risk of decreasing diseases among living beings, blah, blah. So much of public attention to the subject sewage. And this public attention to this subject called sewage demands that the people who are responsible to manage a sewage facility or design a sewage facility or operate a sewage facility are well trained about their responsibility. And I'm happy that all of you are actually connected some other way with this important task of sewage water management. So let's try to just put something called current challenge, because there's somebody called CPCB, Central Pollution Control Board in India. If there's some foreign guests, there will be definitely a regulating authority at your places also. That defines the norm for sewage water discharge into water body. That's it. We put a full stop here. Why? Because responsibility of them managing it belongs to the state government bodies. They can upgrade it, they can put more difficult norms, they can also relax it, and there are a lot of things which we are talking about. But in short, if we have to talk about the challenges, we talk mainly about things like pH, BOD, COD, suspended solids, ammonium nitrogen, total nitrogen, and fecal coliform. And in India, you must have aware of a circular from government about 3 different kind of discharge limits they have set for A class city, B class towns, and C class facilities, etc., etc. So there are different norms for different level of the municipality or industry itself. How do we address them? So we address them by understanding our sewage in some major classifications. So let's understand first one called physical characteristics. What is physical characteristics? Something which is measured by physical methods. For example, total suspended solids, total dissolved solids, volatile solids, pH, color, temperature, turbidity, conductivity. Now, something for which you require a chemistry lab and want to go for some kind of chemical analysis is called chemical characteristics, which is chlorides, alkalinity, acidity, nitrogen, phosphorus, sulfates, sulfides, whole lot of metals. Typically, they are less in sewage, but a lot in inelastic. But there could be metals, Fe, chromium, lead, anything. Whatever is used by humans will be available in the sewage. Then there are some chemical characteristics which are of organic origin. Now, I'm not going to describe here what is inorganic and organic. Probably all of our chemistry students, and we have studied 2 chemistries, one inorganic chemistry, one organic chemistry. So the organic chemistry means basically any kind of material or a pollution which has got carbon as one of the material. Essential element should be carbon. That can come out from either aliphatic series or aromatic series. So a whole lot of words which we have already studied, something called alcohol, aldehyde, ethanol, methanol, benzene. You can keep on remembering all those subjects which you have studied in class 8th, 9th, 10th, 11th, 12th. in chemistry chapters to become engineer, those all, if I have to measure one by one, becomes a problem. So how do I measure them? So scientists have devised a method. Okay, take the pollution, boil it with potassium dichromate, and whatever oxygen is consumed, that is known as chemical oxygen demand. So that's one measurement of pollution. The another measurement is, okay, just measure total organic carbon using instrument. So how do you measure organic carbon? You burn all the carbon, it becomes CO2. Dissolve the carbon into water, it becomes H2CO3. H2CO3 is a weak acid. Titrate it with alkali, you get the number. So the TOC is a value of your organic impurities. But what correction you require? If you already have M alkalinity in the water, that means bicarbonate ion or carbonate ion is already present in the water. So to that much level, you do the subtraction. So suppose you get a TOC of a sample as 1000 and alkalinity of that sample is 200, same units, then the TOC is actually 1000 minus 200 because 200 was inorganic, right? CO2 was there in the carbonate ion also. CO2 was there in the bicarbonate ion also. So you want to measure the organic, right? Total organic carbon, not the inorganic carbon. So the TOC monitors need corrections with respect to the M alkalinity which is present in the water. I hope it was not complicated. Then a lot of individual organic compounds, right, can cause volatility. For example, petrol. What is petrol? It's a volatile organic carbon. Why? Because you can smell it. So anything which can start traveling in the environment, right, is considered to be volatile. Some you can smell, right? That's why I call aromatic. Some you may not smell. But something does not smell does not mean it's not volatile. There could be volatile metals which are not causing any kind of smell. Volatile is a term used for a material which can come into the gas phase is normal ambient condition. There could be things like pesticides. These are man-made long chain polymers which are typically biocides in nature, biocidal or germicidal effects, and these are pest control products. So there could be pesticides, which is a concern in a sewage. Why pesticides come into the sewage? You know, India is a very large nation, which largely depends upon the fertilizers. A lot of pesticides and pest control products are used in our field. And if our supply system in sewage is not completely sealed, and if it can get some rainwater into it, so the water from the field can come into your municipal water systems, and the pesticides may be present in the sewage or waste which you are collecting. And finally, biochemical oxygen demand is something which is a measure that if I have to manage this pollution, do I need the help of my chemistry or do I need the help of bacteria? So if I take the help of bacteria and bacteria like a food can eat it, then that point of organic portion, right, is biodegradable. So for any sample which you get into wastewater treatment, it is important for us to check its biodegradability. And the biochemical oxygen demand is one such test to understand the biodegradability of the waste. BOD is not a pollution. BOD is just a number. COD is the pollution. BOD is only an indication how much oxygen I'm going to consume if I try to manage this COD using bugs. So I hope that clarified the difference between BOD and COD. Then finally, some kind of biological characteristics. Okay, if it is a sewage, then it may have bacteria, it may have viruses and all those kind of things. You know, there are lots and lots of report available on the internet how the presence of a deadly material called corona, right, in sewage is the indicator of the community spread. Because if you all are having infection of corona in a community, most of the people, then their fecal waste will also contain that coronavirus traces. And if the municipality gets a high number of coronaviruses, right, in particular sample, they can say, oh, okay, this community who is living here in maybe a city called X, I don't want to name it, and having lots of patients who have got this kind of disease. So this lot of studies were done in France, Canada, and all that thing, how this can be helpful in mitigating and understanding which kind of population are actually getting more effect of this deadly virus. And all this thing is not important. If you ask me from an environmentalist perspective, I may say I do not care about your physics, chemistry, organic or biological characteristics. Tell me, if I put this water into the river, whether my fish will survive or not. That is called toxicity test. So a sewage treatment plant or an effluent treatment plant, if it goes to a toxicity test, it's bad. I put the poor fish into my waste and try to judge whether it will survive for 72 hours without giving any extra oxygen. That is the test. So if fishes survive 72 hours in my pond after sewage treatment plant, so we can say, oh, I've got 100 fishes, all 100 survived, excellent, no toxicity. Believe me, fish does not require the oxygen which I have to give, because if the water is there, the DO will automatically come from the environment. Okay, but if there is lot of COD or toxicity in your wastewater, the DO which is coming from the environment to the water body will be immediately consumed by something which is very tiny. That is our organic impurity, and therefore the DO will be reduced. And if there's no DO in the water, fish cannot breathe, right? We all have studied, no? Fish will take water into its body and through its gills release the water back, keeping the DO with it, right? Class 8th chemistry, how the fish survives in the water is 10. Fish does not need a bubble. We all see a bubble, no? Air bubble. Fish doesn't need a bubble. Fish needs DO, dissolved oxygen. So a dissolved oxygen will be depleted if our waste is polluted. I'm going nice and slow. The idea, again, I'll repeat, idea for my training programs are for you to learn things very, very simply. There are lots of definition available on internet and you can read that, but try to understand it in a very simple manner the way I'm trying to teach. So if you ask me what is the best indication of the performance of my sewage treatment plant, I'll say put a fish pond and grow fish. If fish are surviving, you are doing a good job. Forget COD, forget BOD, forget physics, forget inorganics. Okay, because fish survives in seawater also. So very high salt is not a problem to me. See, I'm looking always, if you remember my treatments slides, I always talk, technology must be for people and environment. Technology is not a medal that I have got my beautiful technology in the plant, right? As long as things are doing its job. The fish bioassay, which is the most ignorant thing in any wastewater treatment facility, is actually a very important way to know the performance of your wastewater treatment plants. Moving further, we have to teach all this. So let's go into a little bit more details. What is called TDS, total dissolved solids? And total dissolved solids, technically on the books is written as two terms called inorganics and organics, some of both. But most of the time, TDS actually is only because of inorganics, because organics does not do any kind of conductivity. So the right word is, I'm presenting this slide because this is the way you will see in the books. But I'm trying to tell, when a layman or when a water treatment technocrat talk TDS, he actually means only inorganic solids. He doesn't mean organic solids. Traditionally, dissolved solids means okay, both inorganic as well as organics. When you look at inorganics, there would be lots of ions when we talk about calcium, magnesium, and all that. Lot of nutrients. And why we call it nutrients is they are the materials responsible for growth of natural vegetation in a water body. It could be algae, it could be seaweeds, it could be seagrass. It's not only algae. In all, if there's a lot of algae growth, it is called eutrophication. So all these kind of materials like phosphorus, nitrogen, nutrient, etc., they are all responsible for what? They're responsible for growth. They are beautiful materials. You give all this material to a farmer, he would be very happy. Actually, what farmer does, he doses nitrogen and phosphorus in his field because he wants his soil to give a beautiful quality grains, food grains and all that. So N and P are not bad thing. But if this N and P start going into your water bodies, which are stagnant in nature because of the sun energy, lots of flora and fauna and algae will get developed. And what will happen is the body, a natural body like a pond or a lake, etc., will start getting a cover on top, right? That cover on top will do what? That cover on top would start oxygen depletion, because oxygen is not touching the water surface now. Oxygen and water surface, there is a cover like a plastic sheet. You understand, plastic is a bad word, but I'm using that. The algae formation on top of algae bloom on top of greenery on top will stop this oxygen transfer. Algae is not bad thing, because it does some good thing also. It reduces the rate of evaporation from the water body. Okay, so it's not bad thing. Okay, anything in our nature, planet, whatever is available is not bad, right? Even sea grasses are not bad, because sea grasses are responsible globally for the highest CO2 reduction on this planet. We are talking about CO2 reductions. So who will consume CO2? Sea grasses. Sea grasses are the largest free technology available from conversion of carbon to a green vegetation. So CO2 is taken, oxygen is released. We cannot even thank that much to sea grasses. All the oxygen which we are breathing right now is produced by some trees and grasses or all the vegetations which is around us, because they will take the carbon dioxide and they will start giving back to oxygen. Now, finally, all the metals, when soluble in form, is in the form of inorganics. And in organics, we have already discussed this: biodegradable organics and some kind of organics which are difficult to biodegrade. Okay. Now, what is TOC and COD? If I have to go a little bit more detail about TOC and COD again. So on top of the spectrum, you can see TOC. Okay. And out of this TOC, whatever is oxidizing is COD. Okay. By using potassium dichromate. So there is a lot of organic carbon, but some organic carbon is not oxidizable at all. It is just inert. You just made it and that's it. So sometimes TOC and COD separate indication indicates you, okay, this is permanent pollution. You can't do anything with that. Okay, this is the way you have to understand. Yeah, okay, sir, you have come to the COD level, which is very, very low, but still the TOC level is this. So something like you would have heard, in the newspaper or in various channels and these kind of medias, a term came about something called microplastics, microgels and microplastics. A lot of microplastic is available in the sea, and fish is eating the microplastic, and it is a hazard, right? Why? Because that is an indicator of TOC, but not the COD. It's not oxidizable at all. Amongst the oxidizable portion, right? This diagram is presented right like this. I do not somehow like it. What can be? So BOD is no number, but BOD is you can be COD has got two classification. One which will be reduced during bacterial actions. So that kind of things we start wrongly referring as BOD, and something which is not biodegradable, we just keep it like that. And a technical term for that is NBCOD. Okay, but what a COD minus NBCOD is not BOD. Yeah? So by this formula, you should not understand that COD minus NBCOD is equal to BOD. No, BOD is just an experimental number. The right term, I should write on this slide, BOD is BCOD. Thank you very much, Twinkle. So next time we'll improve this slide. Okay, so we should write BCOD here, not BOD. Okay, out of this, when this use this BCOD, which is a very good word, out of that, when whatever oxygen you will consume, that you will start writing BOD. So COD is the amount of oxygen consumed to chemically oxidize organic matter, water constituent into inorganic end products or carbon dioxide. And then we have something called soft BODs, hard BODs. These are the diagrams which we use from various presentation slides or internets and all those things, even textbooks at times. Idea is that you have come through this kind of diagram, and when I give an explanation to you, you will understand. So amongst BOD, suppose, which is typically a term called PCOD, what is the meaning of soft BOD and what is the meaning of hard BOD? Let me explain to you. For example, you have sugar in your waste. So sugar is very easy. Bugs will love it, right? It is really hydrolyzed and immediately they'll start consuming it. So the right term of soft BOD is RBCOD, readily biodegradable COD. And some large molecules or even some particulate molecules which will take some more time to hydrolyze. Okay, for example, my saliva, so these kind of things which takes a little more time to hydrolyze first and then be readily available for bacteria to intake, then we start calling them hard COD. What is biochemical oxygen demand? BOD is the amount of dissolved oxygen that microbes need to break down organic matter. Understand? This is the right definition, absolutely right definition. BOD is not a pollution. BOD is the oxygen required for microorganisms to do their job properly. Higher organic biodegradable matter, lower oxygen supply of oxygen increases. Okay. So when we are talking about BOD, some more slides, I'll go into more details, then you will be able to understand that the BOD actually calculates the three different levels of oxygen, and that is a sum of something called, technically I'm just speaking right now, at the right slide I'll say oxidation, synthesis, and endogenous respiration. So the three type of oxygen is required by microorganisms. First is oxidation, second is synthesis, and third is endogenous respiration. So the BOD is sum of these three oxygen demand for a particular sample. Okay, so this is a very, very interesting slide where we have tried to put to you what are the unit operations we do in a typical sewage treatment plant and what kind of pollution we have to handle. So we have to handle things like suspended solids, biodegradable organics, pathogens, NNP, colloids and dissolved solids, some kind of VOCs, volatile organic carbon, and at times some odors. And what are the combination of technologies possible? We need to do screening, rate removal, sedimentation, high rate solid contact clarifier, chemical precipitation. That's it. These all first three level of technology would address only suspended solids. The next biodegradable organics would be addressed by aerobic suspended or attached growth, anaerobic suspended or attached growth, some kind of chemical oxidation, some kind of membrane filtrations, all things. Pathogens, that means life. Life requires only one answer, oxidation. You oxidize the pathogen. How do you oxidize? You do chlorination, ozonation, ultraviolet, everything. Actually, it's an oxidation process of killing the bug. The nutrients, NNP. Okay, here NNP nutrients removal, one can achieve by something called breakpoint chlorination. Like you put so much of chlorine that all your amines are converted into chloramines. So when you convert all the amines into chloramines, then it's a breakpoint chlorination. Otherwise, you can do for biological nitrification or denitrification. One can also use air stripping if there's a lot of inorganic ammonia. Okay. You can also use ion exchange if there is very little nitrogen or very little phosphorus. Colloids and dissolved impurities can be taken care by membranes, chemical treatment, carbon adsorption, ion exchange. Volatile organics. Okay, the best way to remove volatile organics is air stripping, but now the volatile matters comes into the air. Okay, incidentally, I'll just ask a question. You cannot answer me because it's not a live interactive class. Have you seen refineries? On top of refineries, you see fire. Why there is a fire on a refinery? Any refinery, Reliance Petrochemical, IOCL, Hazira, or anywhere, you will find a fire coming out. Always lighting a fire. What actually a refinery does, it will suck all the VOCs from various places possible and take it to a high elevation and burn it there. And when the volatiles start burning there, that means a little bit of suction is created and all the volatiles continuously go into that direction. That avoids any risk, hazard, of fire in the premises. So all the petrochemical complexes, you will find a beautiful, flare on top, and lots of VOCs are being burned. Sometimes people ask, why they are burning it. They are producing petrol, so they are burning VOCs. Otherwise, VOCs can be fatal. So VOCs, the best technology is air stripping, but remember that if you have too many VOCs, so what you learn in your sewage treatment plant don't apply in a refinery. You must burn those VOCs because they are potential fire hazard. And odors can be removed by carbon adsorption and chemical stripping. Actually, when we are talking about odors, here I'm talking about the odor which is there in the water. Okay. When you talk about odor which is there in the sludge, you cannot do chemical stripping or carbon adsorption. So simple odors which are there in the wastewater can be chemically stripped, or can be, you can use the carbon adsorption. So you may feel the training program is already over, because this is what is actually in a sewage treatment plant, the combination of these unit operations to address these kind of problems. Now, how do we systematically do it? We do it systematically via understanding and dividing into certain tools. So there are sections called preliminary, primary, secondary, tertiary, and sludge. These are the 5 goals. One of my colleague, Twinkle, she has put up all this very nicely for me. Thank you, Twinkle, for that. For breaking down the sections into different modules. Preliminary will cover screening, grid chambering, and equalization. Primary will cover all the clarifications, flotations kind of technologies. Secondary means it will go towards all the biological kind of treatments. Therefore, you already treated the effluent. So tertiary is denoted towards polishing your effluent or sewage for further use. And the 2 processes, mainly primary and secondary, will also produce sludge. Preliminary also will produce some kachra, right? Not sludge. Some waste material. Preliminary also will produce like plastic bottles and sand and grits and all that. But it's not sludge. And you will produce sludge. And sludge can be managed by various technologies. So this is overview of the technology. Thank you for selecting to be my batchmate for this particular program for 4 days. Next 4 days, our word is this: 1, 2, 3, 4, 5. So we'll go in depth and take a deep dive into all these subjects. Feel free to ask as many questions as possible, and I want to work whole night with you guys. No problems. Whatever questions you have, please keep sending emails to my colleague Ramya ji, and I won't hesitate, Ramya ji, if you can couple of 25 questions today, and the tomorrow session we start with answer 25, because we don't have a live audience. Now, how do we do that? So we have to put all these unit operations into some place. So I'm just presenting you a typical, diagram for sewage water treatment scheme, which has got influent, screen, grit removal. And after grit removal, naturally the water needs pumping. It can go to equalization basin, or it may go by gravity to equalization basin. Then you do aeration in equalization basin just to make sure that everything equalizes well, or you may use a agitator here. Then you go for polymer addition, Flocculation. Then from there you remove all the primary sludge, which can go to sludge drying beds, and the wastewater which is coming from Flocculator is partially treated. Why partially treated? Because we have removed most of the suspended solids. And if those suspended solids are of organic origin, that means you have removed a COD. And that COD removal is called a word called PCOD, particulate COD. So all the particulate CODs are removed up to this stage of Flocculation. In fact, I just take a turn here and tell you a small story. You would like it. The story. I was part of Ganga Action Plan. Recently you must have understood that there's something called Namami Gange and all that. And I must thank the government officials of this era. Last 8 to 10 years, people like me feel very respected. And I tell you why we feel very respected is because the government have started inviting private people to at least listen to us. Earlier, whatever they used to do in their closed rooms, never anybody asked. So this Namami Gange program was handled by one Professor Tariq of IIT. And we were asked to come there. Okay, we only free lunch was available, all travels and everything. Anyway, we were paying on our own. So we went there, but the good thing they were listening. And I did tell all the people, we were talking about sewage treatment plants and we were talking about the levels of, treating our wastewater to ammonia 10, phosphorus 1, COD 50, and some other people were debating whether it is 250 and all that. One very young person, Sanjeev Srivastav, young in their environment, old with respect to my age right now, but in that environment I was very very young, a novice kind of person. uh, I presented to them a different picture. Other day, if you really go all across the any water river in India, you will find majority of the place even bar screen is not there. Even a dog which dies in a nala goes all the way to the holy Ganges. So do not spend all your money in doing a hi-fi treatment of sewage, looking for big space, primary aeration and all that. You go into phases. And in the first place, at least make sure that the nala is not kacha, it's pakka, so that you can have an authentic data of how much flow is flowing in that nala during normal weather, normal rainy weather, or during incessant rain. You right now do not have any data. You have a hypothetical model. In our entire nation, we have something called hypothetical model, that in some Bible it is written that one person consumes 170 liter of water, so his waste generated is 130 liter. And since the population of Ahmedabad city is this much, approximately this much sewage is being generated in India. That's where we are working. So we are working on a wrong model. So this cut to story short, I said, if you put screens and grit removal, 80% of the Ganges will be cleaned automatically. Don't have to do anything else. But sometimes it takes guts to listen to the new ideas. So nobody listened to me and people are doing what they want to do. But in the first place, all the money should have been spent only for putting screens, grit removal, and let everything go to Ganges. But what government is doing, they are putting some beautiful plants in Kanpur, some in Agra, and then they are leaving so much kilometers of stretch, absolutely no fund is spent. So I would have gone for a systematic engineering method or going only for preliminary treatment, not even primary. Second phase, primary everywhere. Third phase, secondary everywhere. Fourth phase, tertiary reuse everywhere. But government has gone for, okay, we have only this much funds, so 20% of the sewage is treated to a level of tertiary, and 80% sewage along with the docks are still going to the rivers. So you guys decide. In future, you will become, some technocrats and some engineers. What would be your right strategy to treat? Coming back to this, my slide. After secondary clarifier, you need disinfection, then filtration, and after filtration, you can classify it as a treated water. This treated water is of very good use. Now, what we will deal? Now you say, sir, you already taught us this. So what is left to understand? To left to understand is few words. Hydraulic detention of this particular plant is important. Okay, how much time your water is spending from here to here? Hydraulic detention time. Influent to treated water. How much hours or days you are holding your sewage doing whatever you are doing. The second thing is biomass retention, because the bugs are doing the job, right? So biomass retention is very, very important. Buffering and recirculation. Now, these are the two very, very important words. Please understand, we'll go into more detail of this. Buffering means the capacity of this particular plant to buffer anything, because this is not continuous. So sometimes something more immediately can come. So are you prepared for that? How do you prepare yourself for buffering capacity? Whether do you have tightly designed plants or you have a buffering capacity? Okay, secondary clarifier, even if 1.5 times flow comes, no problems. So there the buffering capacity. And recirculation needs means if your waste is not meeting a demand, do you have facility that, okay, part of the stream goes back somewhere here and recirculated, or something which is not performing here, right? Here need to go and recirculated back to the maybe equalization itself. So a small plant buffering and recirculation is very, very important, because I have seen many small sewage treatment plants operating Sir, I have stopped the plant. Why? Because, sir, this tank is not full, equalization tank. No effluent is coming from here. No waste is coming from here. So night shift, nobody sends any waste in a hotel industry. So this is incorrect. So ideally, you put the transmitters here, okay, or level switches here. And if you are reaching a level and you already have a demand, or supply kind of forecast from here, then from here you put this water back to the system so that you start operating on a continuous flow. So it is sewage treatment plant is not cycle or car. Okay, today I'll drive at 20 kilometer per hour, tomorrow 40 kilometer per hour. Sewage treatment plant actually should work on a very fixed velocity and fixed flow rate throughout the period. Now, going further, we understand, I was telling in the beginning, we would have to understand physics, chemistry, and a lot of mechanical and biological things. The sewage treatment plant is a combination of so many different engineerings together. For that matter, any plant is. But sewage treatment plant particularly becomes much more complicated because we are neither dealing with liquid nor dealing with solid, and we are dealing with mixtures. And mixtures also are slightly complicated mixtures. It has got organic content, it has got inorganic content, it has got dissolved content, it has got suspended content. So during this first fundamental presentation, let us try to understand what is the physical things. So when the physics is involved into screening, particle size, shape, specific gravity, sedimentation, gravity sedimentation, centrifugal forces, filtration, flotation, all these kind of technologies, when we talk about, your lot of knowledge on physics will come into picture. When we talk about things like coagulation, flocculation, precipitation, acid and alkali pH adjustments, a lot of chemistry knowledge will come into the picture. And when you have to understand bug behavior, food, nutrients, carbon, nitrogen, phosphorus removal, toxicity, then you would have to understand the biological bioscience. So a good engineer actually is someone who has his physics, chemistry, and biology strong. So all three has to become strong, which is typically a problem. Why I tell you problem, irrespective of the societies or countries, India by and large, at around class 10, you decide whether you want to become a doctor or an engineer. Now, these are the only two choices are offered to the science people. And those who want to become engineer, they don't select biology. And those who want to become doctor, they don't select physics and chemistry. So cutting a combination of physics, chemistry, and biology is difficult. And hence, my today's program and next 3 days program would be dealing that at least fundamental levels of physics, chemistry, and biology, everybody understands. I forgot to tell you, a lot of mechanical engineering knowledge is also important in this particular business because you are dealing with other equipments like pumps, blowers, and agitators. These are the only rotating equipment. Everything else you forget, right? This is not much complicated business. So if you want to master this business, not a very complicated way to do it. Now let's look about some physical things. So a common sense says sedimentation. A particle sinks if its specific gravity is higher than 1, which is the specific gravity of water. Okay, so when specific gravity is higher than 1, it will sink. Okay, and if specific gravity is less than 1, it will just float. Plastics, papers, anything. There are other reasons why things will float. For example, the entire ship floats. Okay, that's a different science altogether. वो बाद में सीखेंगे. That we'll understand a little bit later. But simple thing is, if it is less than 1, it will float. If it is higher than 1, it will sink. And it will remain a sediment. It will never come up if it is much, much higher than 1.5. If a specific gravity is quite high, for example, 1.5 and above, that material physically, it will remain sedimented only. It will not even travel within the river. So do you want to flood your rivers with a lot of material with very high specific gravities? The answer is no. Otherwise, in their bed, they will all keep accumulating and there will be issues of desludging or desilting of the rivers. Just getting a little bit more details into this sewage treatment plant, why particle settle. So I would have to take all of you to class 10, 11, 12 physics. You have a ball here. You can see that. So this is ball which is dropping. If it is a gravitational force acting on this, which is actually mg. If I have to write, I'll just use the pen so that you are more comfortable. So if this is mass is m, so this becomes mg, right? Everybody knows this. And drag force. Why this drag force? The drag force is because this particular material, when it is coming down under the influence of gravity. So what actually it is doing, if you remember physics, it is accelerating, acceleration. So when it is accelerating, it is disturbing the air here or water here, whatever it is. So that air and water will say, no, 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 please don't disturb me. I'll put a force called drag force on you. So that drag force is F. So when F is equal to mg, okay, F is equal to mg. That means both the forces are neutralizing each other. So the particle cannot accelerate anymore. At that point, particle cannot accelerate anymore, but it must have attained some velocity, v. So this velocity, which is attained at the time that I am no longer accelerating, is called terminal settling velocity. This terminal settling velocity was studied by a scientist named Mr. Stroke, and he defined this F V mg here. You can see P TSV is equal to rho 1 minus rho 2 a square g divided by 18 mu. So what it says is your velocity at which your particles will start settling depends largely upon two things. A, which is the diameter of the particle, and rho 1, which is the specific gravity of the particle, nothing else. Because rho 2 is fixed water for a given temperature, mu is fixed, and g has been long fixed, 9.8. Everybody remembers that. So there's nobody you can change this. So this rho 1 is very important, which is the specific gravity of the particle. And the second thing is very important, diameter of the particles. So whatever physics knowledge we have acquired in class 11, please believe me, two technologies. One is called clarification, second technology is filtration, right? The basic of those two technologies, only this formula, nothing else. So if you are comfortable with this formula, you are good at clarification technologies and filtration technologies. What is the role of pump and blower? You can see very simple. Water will always flow from a higher altitude to a lower altitude. But imagine the water is here. Then what you require is you require to suck the water into a pump, and pump will discharge the water. So there is a suction lift, there is a discharge lift, which is called head. This is for pumps. Same thing is with air. Air is available everywhere, right? But you want to give this air all the way bottom here up to maybe 6 meters deep. So you require energy to release a bubble here. So therefore, blowers are used in aeration, in secondary technologies. The key points are energy efficiency of these blowers, integration with the targeted TO level. Okay, that's where the role of variable frequency drive will come. Energy optimization. Okay, and in pumps, you have choice of positive displacement or centrifugal. So all the dosing pumps typically are positive displacement, and all the service pumps are typically centrifugal in nature. For example, your pumps going from equalization to primary clarifier will be centrifugal. But if you are dosing maybe polyelectrolyte, that will be a positive displacement pump. Good so far? Let's move further. Where else the physics will be important? The physics will be important in some areas called agitators. So agitator appears to be a very simple device. You take a shaft, you put a blade, you put a machine on top, and you keep rotating it. That's it. But it's not as simple, because this agitator, this particular blade is subject to the torque. And this torque could be very, very high depending upon how big is this blade. And typically this blade is used in our primary clarifiers or secondary clarifiers. And this shaft therefore becomes very, very important, because imagine if this is a clarifier, okay, where we have put, and this clarifier is maybe 3 meters deep, 3 meters deep. Then what we are trying to do is, if this shaft breaks, You have to drain down first to the 3-meter water before you can do any servicing. And where you will put this effluent now? And therefore, I use the term called buffering capacity. So if you have plant designed like this, you should not keep on working up to this. If you can keep some space for buffering, right? In case you extra effluent has to be parked somewhere in the system, that's where I talk about buffering design. So the agitators are very important, and only thing important is torque. So agitator in primary and secondary clarifier need care with respect to speed and torque, because sludge consistency, everybody wants thicker sludge, but thicker the sludge, problem here. So you cannot thicken the sludge in your clarifier. So you have the sludge at a particular concentration, or right term is consistency, in your clarifiers, and if you want to thicken it further, you would have to wait. And type of solid also is very, very important. Okay, if those solids are something which can do any kind of abrasion here, then it is not welcome. Any kind of abrasion here, then it is not welcome. So agitator designing also is an interesting subject where we will be paying attention. Now let's talk about some of the chemical processes. So you all have heard a term called coagulation, which is actually the process of charge neutralization, nothing else. Just understand is what charge neutralization. Impurities present in the water carry negative charge. So suppose this is the impurity which is carrying a negative charge. So can you have only negative charge? The answer is no. There would be a positive charge nearby, right? So this will be electroneutral, but bulk of the material here is negatively charged. And same is the case here. Bulk of the material is negatively charged. So these two particles will always repel each other. So what is our role? Our role is to neutralize this negative charge. And how you can neutralize the negative charge? The answer is very simple. Put somehow the positive charge. So if you put the positive charge, they will become neutral. So coagulation is a process which is conducted by alum or ferric chloride to avoid this. Most of the time in sewage, it is not required because it's already coagulated. And most of the time, it is required in tertiary clarifiers because there the particles again require little bit of coagulation. Second step is flocculation. The flocculation means things very simple. These are the particles which are coagulated. Maybe 1, 2, I'm just trying to draw. These are the particles which are already coagulated. So they will come on their own near each other because of van der Waals forces of attraction. But if you want them to do it much faster, if you can provide a synthetic material like maybe polyacrylamide. So I'm just drawing polyacrylamide here. You can see I have drawn polyacrylamide. So if you put a polyacrylamide as a long chain polymer, it will start binding all these kind of materials together. And that process is known as flocculation. Flocculation is a process where you bind the coagulated particles already. So coagulation is a previous process. This is the process which is coagulation, which is only a process of charge neutralization. There's one tiny material and then one tiny material. They are neutral now. They are not repelling each other. Okay. And then now if you want to hook them together, then process called flocculation. These are very simple chemistries. It's a little bit more you can read yourself. And once you understand coagulation and flocculation is different, now you understand precipitation. Precipitation is a beautiful thing. Okay, most understood subject. What is precipitation? So I'm drawing something right here. There's a material I like, calcium, everybody knows. There is a material like carbonate. Everybody knows these two materials. Now, if I keep on increasing the concentration of calcium, what will happen? One fine day, they will say, I do not have enough space in the intermolecular space. Intermolecular space, I do not have enough space now. Let me come out of the intermolecular space. Now, from intermolecular space, where the materials are dissolved in form of ions, ions cannot come out. If ions want to come out, they will be asked, please take one anion with you. Only cation cannot go out of intermolecular space because I cannot have a suspended charged material, very tiny. So what happens is from intermolecular space, when they come out, they join together as calcium carbonate. So one fine, very small nucleus of calcium carbonate will be formed. And if there's so much of calcium carbonate, all this will appear suspended. So you can see the suspensions, blue color, red color, green color. This is just to show the picture. Precipitation doesn't happen the way it is shown here. Okay, these are just some kind of graphical photographs. So if anything from solution comes into a tiny suspended matter, then it will become suspension. And over a period of time, this suspension will settle down in the form of a precipitate. So this is what is important. If you sometime study with me in a training program on cooling water and boiler water chemistry, I'll get into more detail on what is precipitation and how it is a process which is related to not only the concentration of the material, but also on temperature of the water. This everybody knows, and most of us know it wrong. We know this pH. So, Sanjeev sir, why you are teaching pH? We know 7 means neutral pH, and as you keep on adding acid, it becomes acidic pH, and if you go down, it has become alkali pH, and pH is equal to negative log H ion concentration. Now, this equation is wrong. Please never use it. This equation is 100% right, when it was invented. But this equation is for the pure water, where you go for hydrogen ion concentration. In our water, alkalinity plays an important role because of CO2 buffering. So water plus carbon dioxide is H2CO3. So here CO2 is a gas, but here CO2 is a molecule. And this molecule can have conductance by H plus, comma, HCO3 minus. Okay, you understand? So if this material is like this, then it doesn't affect this scale. But if this same material is like this, then it is affecting this scale. And therefore, a new equation for the pH, which is the empirical formula, is pH is equal to 6.3 log of bicarbonate as calcium carbonate and CO2 as CO2. This is very, very important to understand. In wastewater treatment, this equation is used to change the pH. So if somebody has to ask me how much acid, how much alkali need to be added to change the pH, you have to use this particular formula. And if you want to use this particular formula, you must know what is bicarbonate. So you must know two relationships. M alkalinity is equal to bicarbonate plus carbonate plus OH. That means any kind of alkalinity is measured by methyl orange. And only hydroxyl alkalinity and half of the carbonate alkalinity is measured by P alkalinity. So if your sample, somebody says P alkalinity is 0, sir. So I'll say, okay, no problems. If it is 0, there's no OH because it cannot be negative. There's no carbonate. So all the alkalinity is bicarbonate. So whatever M alkalinity number is there, you can put it here. Now you get two numbers. You already know bicarbonate. You also know 6.3. Okay. You also know pH of your sample. So if you know 1, 2, and 3 things, only thing what you can know now is CO2. So by you solve this formula, you will get CO2. Got it? This is a very simple way to understand what is the pH of your water, and at that pH how much CO2 is there, and then this formula will be used also to change the pH. So I have to give you a simple exercise to you all guys, and you will solve me today. If you are a good student, tomorrow in the chat box or whatever, you should give me an answer of this. You're right, the pH of this water is 6.7 and M alkalinity is 150 milligram per liter. P alkalinity is 0. Again, I repeat, P alkalinity is 0. Now you calculate the requirement of NaOH to raise the pH to 7.8. Very simple exercise I have given. And my hint is, you please estimate CO2 first. And the second hint is, understand, excuse me one second. It's something more important than what I'm doing. Why you guys are talking? understand impact of NaOH dosing on alkalinity. Okay, so once you do that, now you will be able to calculate a very basic thing: how much acid or alkali required. Now, some students tell me, sir, how does it important? We can do the experiment and find it out. So remember my word, and please remember throughout life: engineers don't experiment. Leave this job to scientists. In engineering, we have been taught that there is a formula, there is a method for everything, and always follow that method rather than experimenting. Imagine we start construction of bridges by experiments. So there is a civil engineering department who has got each and every formula worked out, each and every drawing and document worked out. Then only they make the bridge, because we are responsible people. So engineers don't experiment. Engineers try to find the formulas, calculations, and say, hence proven the alkali requirement is this much. Okay. So this simple exercise you will do, and we will talk about it tomorrow. The next thing is something which I really love about sewage treatment technologies is microbiology and the bug behavior. These bugs, to keep them happy is an engineer's job. Now, this is the problem. We all are engineers. Most of us, probably out of the course registration of so many people, if I have to do a survey, 90% plus people will be engineers. But engineers have to do a job of nursing microbiologist. And why I want to do is because who does your job? The bugs do their job. So what we know is bugs eat. It is not true. Bugs also breathe. Okay, they also swim. They also reproduce. They also die. They also compete with each other for food. The way our kids compete, no, I will take chocolate or I'll take chocolate. The same way the bugs will compete for food. And finally, bugs are killers. They will hunt. Strong bugs will eat less strong bugs. So understand, what is our job? We keep them happy because they are like humans. It's very important science, very, very beautiful thing. In fact, on this note, some of you might be very senior in your organization and learning large-scale sewage treatment plants or wastewater treatment plant kind of facilities. I pose a question to you. Do you have microbiologists in the team? If your answer is no, please hire one as quickly as possible. Because for your health of a good sewage treatment plant, the microbiologist is an important team member in your engineers team. Because microbiologist is very, very important person to understand his bug behavior. We may learn it, right? I may become a doctor, but injection will be given by a nurse only. So there is a role of a microbiologist in the team, and one must have a microbiologist in a large-scale sewage treatment plant or effluent treatment plant. So biological processes do C, N, and P removal. And in this C, I have deliberately put a lot of coal and carbon. This coal I am not looking for. Right? This coal is energy. But the other form of coal we are not able to see. Everything around us is carbon. Right from the time you get up, now, whatever you eat is carbon. So carbon is not a bad thing. Carbon, if in reduced form, it is a problem. What is the reduced form of the carbon? Most important reduced form of carbon is CO2. It is already consumed 2 oxygens. So the moment this CO2 is taken by tree, the carbon goes into the tree body and oxygen is released. That happens for the free. And therefore, this is the importance of the biological process. Biological process is as important process as done by tree. Oxygen is consumed by carbon. Oxygen consumed by pollutant, which is called carbon, and for due to which the oxygen level decreases and aqua life suffers. The thing which I was explaining, if there's no DO in the water, the fish cannot swim. So our responsibility is to do a good biology, because microbiology is responsible to convert that soluble organic carbon, soluble COD, into a particulate COD, and then it is very easy for you to remove the particulate COD. Biological processes also have a balance of food and nutrients. So what is the food? So you can see a beautiful star, right? The food is BSCOD, biological, biodegradable, or biological soluble COD. Soluble COD. Particulate COD is not the food. Bugs are like our kids. They cannot eat bread. They will only drink milk. So bugs require only soluble COD. They do not touch particulate COD. They will wait particulate COD to one day become soluble COD, then only they can digest it or ingest it. So microbiology, we have to understand the role of food, which is typically my BSCOD, which is the food. Okay, one second. BSCOD is the food, and beyond BSCOD, if I look at nutrients, then N and P are the nutrients. So in our class, we will address about BSCOD, and then we'll talk about N and P. If N and P is not removed, you can see the picture, the lake full of algae. Okay, some kids can still enjoy, but it's a problem. Because if oxygen transfer stops in this particular lake, you can imagine if this area we stop the oxygen transfer, then we are in problem. This area, if we stop the oxygen transfer, because there are a lot of things which are living here, right? And they start getting problem. Finally, a dangerous sign, which is more applicable for effluent, toxicity. Because toxicity is something which will kill the fish. So most of the times, the lack of sewage treatment plant is not a bigger issue in India. The bigger issue is the discharge of untreated industrial pollution. Because you may give things like acetone, isopropyl alcohol, polyaromatic hydrocarbons, acetate, bleach, or rubbing alcohol, motor oil, ammonia, pesticides, furniture polish, so on and so more things. All these things are actually toxicity to what? Toxicity to fish. Imagine if something is toxic to fish, what about my poor bug, a small tiny fellow here? So toxicity is something which needs to be avoided most of the time, and I can write one nice toxicity because during the training session, somebody asked this question it is called antibiotics. Antibiotics also is a form of toxicity for my bag. Antibiotics. So if you look at the first module, I've tried to tell you the importance of treatment, various technologies and that. We also talked about characterization of the sewage. Just I'm recapping. What are the control factors which one must address before we think of designing and understanding a wastewater treatment facility? The control factors what we have to understand is, in order to operate a successful wastewater treatment facility, your operator must control, number one, amount of pollution received. So all those impurities which we're talking about, how much you are going to receive. So flow meter cube per day and instantaneous meter cube per day. And second, concentration of the various pollution. Because flow multiplied by concentration will give you amounts in gram or kilograms per day. Then the second important thing I said was hydraulic retention time. How much time is available? At my entry, I get the effluent right now. So I have to make it a treated water. So whether I will make a treated water in 90 minutes or 120 minutes or one day, that is called hydraulic retention time, which is available to me. Third, synergy with plant operation, normal CIP and shutdown. Now this is interesting line. See, most of the time, there is a sewage treatment plant maybe in an industrial cluster. Now industrial clusters or maybe schools or every places, they have differentiating, operations at times. There's sometimes mixed operations. This point number 3 is more applicable for the industry. But even for a small sewage treatment plant design, what is normal? what is CIP, what is shutdown. On day 4, I am presenting a case study of a Bombay, sewage treatment plant, Mumbai-based sewage treatment plant, and this sewage treatment plant is into a business hub where almost 16,000 employees visit every day, and they work in various shifts. They have restaurants, they have cafeterias. So I'll present that as a case study on case number 4. There you will understand this meaning of synergy with plant operation, normal CIP and shutdown. Because typically, entire Saturday, they keep on cleaning everything, restaurants, tables, toilets and everything. Lots of CIP takes place in a good office environment on this particular day. And 4th, the season, summer, winter temperatures. Okay. What works in summer doesn't work in winter. So why? Because my bugs are different. Even for as a humans, the moment you understand the creature, bugs are like humans, you'll understand what I'm saying. The way we are uncomfortable in very extreme cold and extreme hot temperature, same way in sewage treatment, extreme cold and extreme hot is a problem. And why it is important to understand these 4 control factors, only 4. I'm not asking you to do a big job, just 4. Always keep in mind in designing, because these will relate to energy consumptions, your buffering requirements, and finally, the treated water quality. Because ultimately, we are looking for a good treated water quality. This is what is. This is the reason why we are talking about all these parameters. Now, if we have to understand these control parameters from a different perspective, let me look at this point. Each impurity must be understood specifically for its impact on wastewater treatment plant. This is a very, very important line. Do not generalize things. Do not generalize things. I'll just give you a classic example. I was working on a project. I cannot present the case study of that because that's a project where I have some kind of confidentiality obligation to tell. So I'll not name you, but I'm just trying to say it was an airport and it was designed by a beautiful consultant from South India. Beautiful consultant. He's very knowledgeable in his field and all that. But he designed it for sewage treatment plant, the way a sewage treatment plant is designed. And believe me, guys, when this plant was getting commissioned, that day the COD was 230, but the ammonia was 354. He said, what the hell? This is not sewage. And he was absolutely right. Because in an airport, what kind of sewage you expect? The airport will be majority of the concentration of the pollution will be urine. And this is called pseudo sewage. Because it looks like a sewage, but it is not sewage. Most of the waste at the airport is urine, not the fecal waste. So there is not enough COD waste. And in airport, you don't cook. So you don't have a kitchen waste. In airport, whatever solid waste and kitchen is all use and throw kind of plates. So it goes into the dustbin. So there is no carbonaceous source itself in the wastewater treatment plant. An entire wastewater treatment plant was a big failure in a very large airport. And ever since people learned, nowadays, last 10, 15 years, whatever airports are being constructed, they know it has to be constructed on pseudo sewage rather than the sewage. So each impurity must be understood specifically with respect to its impact on your wastewater treatment facility. And it's the unique control factor impact processing. For example, you will have to deal with particulates, inorganics, biodegradable, floating, these kind of impurities. You have to understand the process by which they are getting generated. Okay, what is the process happening? Now, process is not a term for industry only. We are having washing, cleaning, and all that. Process is even a process for the humans. For example, if you go to your office, do you take bath there? Answer is no. Most of the time, you only go to toilets and maybe gargling and maybe toilet flushing and things like that. But no laundry, no washing. So if it is an office complex where only people go, work, and come back, you will not get surfactants and phosphorus. Okay, because which comes from the laundry waste. So you have to understand what input qualification, what we say. Okay, and why you want to all do these things in more retrospect is this: you have to understand what is soluble, what is organic, right? There's inorganic, but there's organic. Whether it is non-biodegradable or biodegradable, how well it can settle, and so many things. Allied means, it's not just end of what I said. There's so many other things which you must understand impurity wise. So first slide, we presented lots of control factors with respect to flow, hydraulic detention, synergy of plant operation, seasonal variation. The second, within the impurity itself, get into detailing. That is what this slide says. Because if you wanted to understand overall sewage treatment plants, the impact of certain things called flow rate, concentration of impurities, temperature, shock loads, how does it their variation, either plus or minus, either variation, even minus variation. Somebody will say, oh sir, flow has come down, so what is the problem? No, big problem. If the flow has come down, the food is come down. If the food is come down, my bugs are there, they will feel hungry. So there is this is general slide. I'm not going to too much of detailing. So flow going down means hydraulic detention time goes up, energy consumption goes down, buffering capacity and recirculation need is not there, and treated water quality improves. But if the flow goes up, the treated water quality goes down. So it is a very, very important slide to understand with respect to what is the impact of whatever we are trying to do here on something called what is going to happen in this area called this particular portion. Hydraulic detention, energy consumption, buffering, and treated water quality. So this kind of charts I'll produce more with respect to other technologies also. But overall in sewage treatment plants, 4 to 5 things can really impact your energy, retention time, buffering needs, and treated water quality. Yes, now I'll go for my next presentation, which will be typically for 1 hour, maybe 1 hour, 5 minutes. Preliminary treatment, module 2. So module 2, 1 is the fundamentals. We go into preliminary treatment. And this will be a quick rush, right? It will not be a very, very elaborate session because designing and all these things will come on a later date on all same session when we talk about a module called Process 7. So we describe the primary treatment objectives, what are the functions, key settings and control points. We explain the control factors relating to preliminary treatments and understand some kind of troubleshooting metrics into this particular objective. Now, this is something which I love this slide. So it is divided into certain areas. We say headworks. What is headworks? Means just on the plant inlet, whatever you have, screenings, grit removal, and FOG removal. If you have excess fat, oil, and grease coming to you, then you go to equalization. You put a star here because equalization tanks are usually below grounds, and then you do pumping. And my ideal plant designing will be that after that, all the systems should be hydraulically designed in such a manner that you do not require any further pumping. Then what we are targeting ultimately is your floating matters, oil and grease, fat, grit, TSS turbidity, a lot of particle size come into picture, and a whole lot of equipments are going to follow pre-biology, which is flash mixer, flocculator, clarifiers, typically a DAF, and some kind of sludge management. Now, what is the meaning of this black line here? So the meaning of this black line here is it is preferred that this point onwards, star onwards, the entire system is working on a constant flow. So someone was asking me this question during the mid-session break about the constant pumping or whatever comes pumping. For a very large municipality, the equalization becomes unaffordable. You can't just afford the equalization, right? So there we have no choice but to really treat whatever comes and develop the necessary SOPs for that. It is not that you put whatever it comes. It is already planned that whatever is coming, then how we will handling it, right? So as the level goes up, as the flow meter goes up, one more pump starts and some recirculation stops and all those kind of logics are developed in that particular sewage treatment plant. Headwork means screening, grit removal, and FOG. because this will be designed on the peak flow, maximum flow possible. Because you cannot ask people to hold the waste before this particular point. An important thing, therefore, becomes is the screening. Now, when it comes to screening, there are several things which come into picture: the screen size, the screen angle, its cleaning frequencies, head loss through the screen, and important most thing is the velocity through the screen. Why velocity is important? Because I do not want accumulation at the screen itself. So velocity should be such a high velocity that whatever we intend to screen, for example, plastic bottles or some kind of heavy particle size materials, the the cap of the plastic bottles, etc. They should stop. Maybe gutka, pan masala, pouch, etc. These kind of things should stop, but nothing else should stop here. That is also is important thing. So you require enough flushing velocity, and that determines something called hydraulic loading rate of the screen. During the design class, we get into the design. Okay. Sometimes something can be very simple. For example, there's something called a bucket screen. So there's a bucket. You can see some kind of mesh here, and large size particles are getting arrested in this bucket itself. And these buckets, one working, one standby, are being used by someone. What is the screening goals? Principle is screen is to remove coarse material from the flow. Okay, restrict flow and create flooding in the plant drains. That's important area, because you cannot create the screen in such a way that it will create flooding back. So it's a very coarse level of technology. You will let the impurities stop, but water not to stop. Water has to flow from there. And you cannot put, okay, sir, screening is important, let's put the finest screen possible. No, that finest screen will choke and the entire plant will be flooded back. Okay. And you have to avoid the damage to subsequent equipments. If a larger particle goes, for example, a very big particle goes to a pump impeller, and it may damage the pump. And sometimes you can have a beneficial use of biosolids. For example, if it is a kitchen waste, the screen provides a very good opportunity so to really screen out things like rice left over in the thali and some vegetables, boiled potatoes and everything. Anything can come, and a proper screen can be designed there. What are the target impurities? There are so many target impurities: human, industrial thing, and natural waste, and all those things, and lots of contaminations. It can be racks, papers, plastic, food leftovers, hair, net, rubbers, carbon. So many things. Carbon means that does not mean pollution. Carbon means some industries or some sewage treatment plant facilities, they don't have any carbon. But if it is the industry, there could be a material like carbon into this impurity. Okay. So how do you classify a screen? The screen classifies into two varieties. One is coarse screen and one is fine screen. And when you look into coarse screen variety, you can have something very simple like hand clean, then mechanically clean. And in mechanically clean, they have various options: chain driven, reciprocating, catenary, and continuous belt. All the 4 options. Now, these are the simple equipments. Most of the time, if you ask me, sir, teach me how to design each and every equipment. So my answer would be, sir, I do not know, because the screens are designed by the screen vendors. So what are the right informations to be given to them is something which in our hand, that my minimum flow will be this much, maximum flow will be this much, my suspended particle size would be this kind of range. And typically we have racks, this and that. And so a little bit of experience we have to share with them. If you just inform, I do not know, it's a 20 MLD sewage treatment plant, just give me a screen. So he also doesn't know which screen to be given. So a little bit of intelligence has to be provided to the vendor. And bar screens are the manual, just bar, just put some bars for a bigger obstacles. When it comes to the fine screen areas, what we call fine screen, typically when you start going 0.5 micron and below, then we start calling it fine screens. We have static wedge wire, we have drum, and we have step screen. All the 3 possibilities are there. These kind of screens are less used in sewage treatment plants. But I cannot create a separate PPT for sewage and waste right? So this PPT is there, but I'm just informing you these kind of screens are less used in your sewage treatment plants. You typically do not use fine screens into fine screens where you use is because you understand there's a granular material already available in your waste, which could be in a size of 1 mm itself, but it is highly hydrolyzable in nature and will unnecessarily disturb your biology. Better remove from here. For example, fermentation industry, the bread industry, the food and beverages industry, they have lots of biological substances which can be filtered out via fine screens, okay, rather than being put into primary clarifier or secondary clarifier. So how you put a screen chamber? So we can see there's an inlet pipe here. You put the inlet pipe, then all the debris will be collected somewhere here. You have a coarse material, you have a screen, you can just put the screen. This you see 4 number is the bar screen and 5 is the effluent channel. So as far as this screen is concerned, I'm just driving this area. This screen, the water goes out. You can see the difference in level, right? Slight difference in level in these two. And this is the head loss of the screen, okay? Then you have an outlet pipe and you can have some kind of platform where, you can stand and periodically clean the debris, something like that, okay? This is a very simple example of a screen chamber design and how do you put the screens. Now, in terms of the screens, you can see this is the one kind of a scheme. This is a flat bars, and this is a square screen, the square pitch, and certain level beyond, we go towards micro screens, so don't go. So we remain in bar screens and coarse screen. These are the two areas which are more important for us. Typically, we keep 60 to 80 degrees angle inclination. Coarse screens, typically much more inclined, right? Because we have to make sure that the screen removes the material, but they allow water to flow. That's also important. Opening in you can talk about anything. Very big screen is 60 mm, or coarse screen is 20 to 60 anything. Applications, removal of coarse solids such as sticks, racks, and all those debris. And when it comes to fine screening, you are going below 6 mm. And when it comes to micro screening, we are going below 50 microns. These are general classification, not necessarily you are to follow exactly this. In Indian context, Central Public Health Engineering, they issue a manual where they suggest the typical screening should be 6 mm and 10 mm. So this is what they talk about. Now it is kind of screens. So if you're looking at static wedge wire, so this is a wedge wire, which is you fill the water here, water will flow like this and collected outside the screen. And whatever debris materials are putting on the screens are collected here in this bucket. So this is a simple example of static wedge wire screen. They do some removal of suspended matters. They also remove suspended solids to a great level, typically up to 1.2 mm size. You can go 1.2, even 0.2 mm, you can go for this kind of screens. Application, most of the time, it is in the primary treatment systems. These kind of screens are important. But when it comes to the secondary treatment systems, you can use both this kind of rotary drum screen, either this or rotary drum screen, even in the secondary treatment system. You may ask me, sir, you have not gone to secondary treatment system and you are teaching a screen. So believe me, we will talk about the technology some other day called MBR. And most of the MBR failures are reported because of the absence of this rotary drum screens before the aeration tank. Because MBR has got some hollow fiber modules, and you do not want unwanted material in the aeration tank. So you may require some kind of rotary drum screens after primary clarifier, water entering into your what we call it is aeration tanks. Okay, and you have some step screen. Some people also call ladder screens, which could be self-cleaning in nature. That means the screens are moving like ladder, 1 step, then 2 step, then 3 step. And when the screen is returning from here, right, at this particular point, you have a bucket and you can collect your debris. So these ladder screens or step screens can be designed for high flow plants. Some people also call it traveling water screens. So it's all the marketing words, all are the same things. What is the limitation of a static wire wedge screen, which is a beautiful technology, is the significant floor area is required for installation. Okay, and you may require its frequent cleaning, because if something is not clean on its own, then people have to put some water spray here to clean the screen, and that water spray becomes additional water to be treated. So this kind of screens are typically not used in sewage treatment plants. In a large sewage treatment plants, you will find most of the time this kind of screen. Okay. And of course, there would be this screen always there. This is the primary function of the screen. So if you look at the wedge wire screen, which is a very most common unit, if you want to see somewhere, you will find it in PepsiCo India. Okay. Why I say? Because what they do, they make potato chips. So when you make potato chips, what will happen to the skin of the potato? So all the potato skin is in the waste. So if you identify in terms of the COD potential of those skin, we are talking about typically the COD reduction by only screening of almost 6,000 milligrams per liter. So a waste sample before screening and waste sample after screening you can get. And this potato skin is a very easy things to be accumulated in the hyperbolic screen. So typically you will find the food industry, the grain industry, the Horlicks producers, the Bonvita producers, they will be using this kind of parabolic screens, typically not used in our sewage treatment plants. Solid separation belts. Now these are the screens which are maximum used in pulp and paper industry. Now when I'm treating you, if you see me, you only teach me sewage treatment plant, but then I may not be able to cover a lot of technologies. So this design is very specific to the vendor. But what happens in this kind of design, if you see, there's a feed hooper which feeds the your water into two belts, in between two belts. So what happens is the water goes out, and what you get here in a paper industry, typically what you get fiber. Now fiber is a value for them. Please understand. Fiber is a product by which you make the paper. So if the fiber is coming in the drain, the first thing what you do is you put a solid separation belt and recover the fiber. Otherwise, this fiber is a problem in both primary clarifier and aeration tank. Same is the case in the textile industry. But textile industry does not have fiber as a value back to the process. Why? Because this fiber is come because of the fabric washing and fabric cleaning and fabric spinning and things like that. So the fiber does not have any value for them, so they will not put this in it. But most of the pulp and paper industry in your wastewater treatment facility, they'll put this solid separation belt first, and then they'll go for the wastewater treatment plant. Rotary drum screen. These are the lovely screens. Again, I love them. Them screens. These are the screens which are mostly used in MBR. Now, what is this screen for? These screens are for removing bulk of the material, giving the outlet here, and most of the impurities remain inside. Now, this inside screens, when the impurities are inside, you have something called shower water, and you keep on cleaning these screens as well. So if it is the use of this particular screens, this is preferred before MBR. Most of the time, this screen is preferred before. Yeah, again, its design is more specific to the vendors. How do the design? There are many companies who provide the rotary drum screens, many in India, many abroad as well. But major function of this particular screen is to remove the debris and the particles, which could be slightly sharp, which may not appear to be very dangerous to you, but it can be dangerous to the your MBR membranes. For example, simple things called hair, human hair, which can look very simple material, but human hair, if it is too much in the aeration tank because of whatever reasons, they will create something called knots, KNOTS, knots on the membrane fiber. And since they are very sharp material, the human hair, they may cut the fiber itself. So human hairs, same is the case of the pouches. We in India, a lot of people eat gutka pouches. So those pouches are very fine aluminum kind of material, and once rubbed, they become sharp, and if they have the potential to cut the skin. Even things like plastic ropes, packaging material. We have a lot of small plastic, very tiny plastic. So that plastic is a problem for my aeration tank. So all those things need to be removed by rotary drum screen before you go into area like membrane bioreactors. So what we typically do is, so if you look at the control factors about this screening as impurities, what we are looking at, again, we see, if you see my module, each and every place, the unit operation must be related to certain targets. So we are talking about hydraulic flow rates, we are talking about screen sizing, we are talking about how to clean the screen, and finally we are talking about screen sloping, what degree of inclination the screen should be put. Typically, we have bar screens where particles we address to 6 mm and 10 mm kind of particle screens. Typically, you should design it for 2x of the plant flow rates. So if somebody is asking me, how do we really consider what is the peak flow? So the Central Public Health Engineering Manual provides what is the peak flow for various capacities. The data has been collected here. So if you don't want to refer this data, just go for twice the capacity. So if you think your plant is 5 meter cube per hour, your screen should be designed for 10 cubic meter per hour, as simple as that. Typically, 6 to 10 mm simple bars are used here. Cleaning, okay, you have to do manually and typically per shift once, not enough. And 60 degree from horizon should be the screen sloping. When it comes to parabolic screens, typical impurities are peel. So in a hotel industry with a lot of vegetations is possible, food industry, all kind of peel material, right? If you have typical target impurities peel, which you can go 0.5 to 2 mm, 1.5 times of the plant flow rate requirement. You can have a 500 to 2000 micron wedge wire. So maybe you are talking about 2 mm to 0.5 mm kind of filtration from these screenings. You have to put shower water once in a shift to really clean these kind of screens. And screen sloping is not important because these are hyperbolic screens. But till this section, we are talking about the screens which are more, the static screens, where there's no moving part to either clean the debris or there's no moving part to keep the screen clean. So when it comes to automatic screens, it's always better to refer to that screen manufacturer's control, advices on that particular design. So when it comes to more again the control factor of the screen, so there are two things control factor. One is operational and second thing is called performance. So they have to do the performance with solid removal. So they should be good at that. But they also should not create any velocity problems or head loss problems. So if the flow rate goes up, the velocity goes high, and head loss also through the screen goes high, right? So it should not happen that the screen is getting choked. High head loss is very, very high. So if head loss is high, that means the level at the front of the screen will increase, and that will create the backflow. So one has to design to avoid that. That's the only control factor. Screen sizes are important for head losses, but they do not have any velocity-wise consideration, because once you fix the screen, the size is already fixed. Same as the screen sloping. Once you fix it, the slope is not important. But they will be operation-wise responsible towards head losses, and performance-wise responsible towards solid removal, etc. So this in short, we have to understand when we are impacting a particular technology or a process, how it is going to affect your day-to-day performance for which it is intended, or day-to-day operation for which it is meant, right? So these two, operational and performance qualification with respect to the control, need to be well documented and then taken a decision on that. Grit removal, like grit, you can talk about what is grit. Grit is basically a material which is heavy in nature, in short. If you product accumulation of high settling sandy materials, right? The removal of sand, metal pieces, and heavy debris, because it will be only to protect the pump wear and tear. Okay, you are going to pump things, so it's better you remove all the grit. How do we typically design a grit chamber? Okay, so in this particular slide, I'm trying to show you how it is designed. During the design class, we will be covering the design part. So you feed the water in the inlet zone. Okay, and this is the water in the outlet zone. So this this area is the settling zone 3. Okay, and 4th is the sludge zone. That means the settled solids will be taken out here. So this is the way a grit is designed. So in a grit chamber, when we are talking about the water goes we try to keep the velocity, okay, VC, in such a way that that velocity is not taking my settled matter here. That's it. That's the simple criteria which we used to be followed. So balance, when we show you the Excel, you will be able to understand this particular thing. So you can say typically this is the way somewhere in some large plant, so much of grit has been collected. Typically VS greater than VO totally removed. Okay. VS less than VO partially removed. So that's what is VS and what is VO. These calculations we will be doing in an Excel sheet subsequently when we are talking about the process part. This is just an example right now here. I'm not going to run through this Excel sheet today. The Excel sheet, we will be using it, but what we talk about is how many number of grid chambers are there, what is the computation of setting velocity as per Stokes law. So we know the kinematic viscosity of the fluid. Then we assume a particle size diameter. For normal grid, it is allowed that this is the particle size. If you want to go for a finer particle, you can just write, but this is acceptable. Then we talk about settling velocity and blah, blah. So I'm not going to explain this particular sheet right now here. So there is a way you calculate, and then you say VH is less than VC, so this design is okay. So this kind of designing are also possible using McAfee, an engineering book, and also possible by using Central Public Engineering's design manual. But my company has developed some small tools. These all tools will be given to you on day 3 before the sessions, because once I'm working with these tools, you will be able to correlate what we are talking about. And naturally, I must say that there are so many tools which I'm going to hand it over to you, and we have to practice all the tools and work to all the cells. Then I will request organizer to organize a class of 30 days. So it may be difficult, but I'll share those tools with you, and you are free to ask me questions, not only during the program, even after the program also. My office will be able to answer those questions to you. Then there's something called aerated grid chambers. See, sometimes what happens is a little bit of turbulence is important. Now, these aerated grid chambers are typically not used for a very small plants. These aerated grid chambers will be used for a very, very large sewage treatment plants where you want to assist better cleaning by providing air along with the grid, the water. So in the spiral motion, the liquid will be moving in some kind of spiral motion, and you will put some kind of air diffusers which will continuously keep on washing the grit. What you are looking for in a grit removal, you are looking for grit to be removed. You do not want this grit accumulation. Imagine in this chamber, I'm just trying to show it to you. Imagine in this particular area, you start filling grit up to this, and then also you feel more grit. So what will happen is grit will act more like a sand filter and will start also accumulating suspended matters. So do you like that? No, because the accumulated suspended matter will be creating a problem of anaerobic degradation here only. A lot of bad smells, a lot of bad things, and therefore you keep even this grit, right, slightly disturbed by doing the aeration. You can see the air diffusers here. So this is very important when you want to do only a grit removal, but make sure that all the suspended solids are given. The another way to achieve this, there's no accumulation, is called vortex grit separation. So if you have a vortex motion like this, you will find that only grit is getting discharged from the bottom, and in the outlet, even if there is some debris, they are pushed out. And if there is some kind of scum discharge pipe, you can keep a frequent scum discharge pipe. If there's sometimes some kind of accumulation taking place, so you have an inlet and then the vortex created, sludge going out, scum going out, and also the outlet which is scum free. There could be some scum which can come out like here. You can just see the scum will fall like this, and it go inside and remove like this. So it is basically a beautiful design, the vortex grid separator. If you want to see it in operations, you can see it as a LNT design plant in a place called Bhatpara in Kolkata. Beautiful vortex grid separator designed by them, and it's very much functional there. All these figures typically come from Central Public Health Engineering's manual, so you can very easily access these kind of technologies. Bye-bye, everybody.
Yeah, thank you, everybody. Have a great evening. We meet you again tomorrow at 3 p.m.
Yeah, bye.
Thank you. Thank you, Mr. Sanjeev.